Today I'd like to introduce you to a new coordinate system. You've been using the XY coordinate system for a long time. It's sometimes called the rectangular coordinate system or the Cartesian coordinate system after René Descartes, who first used it. Anyway, I want to talk about the polar coordinate system now. The polar coordinate system is based on a couple of things. One is you start with a point, which we'll call the pole. And then there's a half line, which is chosen, starting at the pole and heading off in some direction. This is called the polar axis. Okay. Now, given the pole and the polar axis, I'm going to come up with coordinates for every point in the plane. So for instance, here's a point. And what I'm going to do is I'm going to look at the distance away from the pole, that's called r, and I'm going to look at the angle that you would have to rotate from the polar axis to that line segment. Okay, and we'll measure angles positively going counterclockwise just as we have, and negatively going clockwise. Okay, so the same way. The polar axis can be in any direction, the pole can be anywhere, right? But as soon as you choose a pole on a polar axis, then you've determined how you're going to measure your angles. Okay. So the coordinates of this point would be r comma theta. It looks like x comma y. It looks like just a pair of numbers, but we need to know that when we're in polar coordinates, the first coordinate will be representing the number which is the distance away from the origin, and the second coordinate is the angle from the polar axis. Did I say distance from the origin? Distance from the pole, right? That being said, we will quite often, and we'll do this more in the next video, but we superimpose the XY coordinate system and the polar coordinate system quite often. Sort of the standard way to do it. If this is X and Y, then what we do is we choose to take the pole at the origin and the polar axis in the direction of the x-axis. So then all of your stuff in polar coordinates is like we did it before. R is this distance from the origin. Theta is the angle measured there. Okay, we'll look at that more closely later. But let's just take a look at how we do this, how we plot points, what we do with things. I should point out here, I'm going to scroll down to the next page where I have a polar graph already here waiting for me. This is polar graph paper. This is marked off in degrees. 0 degrees is pointed in what was normally the positive x direction, right? And 10, 20, 30, 40, 50, this is marked off in degrees. Notice where you can see the background of my paper here is the old XY grid. You know, each line horizontally represents a particular y value with x changing, but y being constant as you move along horizontally. Vertically, you're talking different y values for a constant x. Well, over here, the grid that we do, each one of these circles is a constant r value. You're staying the same distance away from the origin, but you're changing your angle. Along one of these radial lines here, you're not changing your angle, but you are changing your radius. Okay, so this is the grid that usually we think of as polar graph paper or polar grid. Right? Now, if I look at a particular point here, let's just, oops, it's not going to like that. Let me see if I can do this. If I look at a point, I want to put a point right there. See if it'll let me do it. Okay. I have to be very careful that I when I just put down a pair of numbers that you know whether it's x's and y's or r's and thetas. So I will be very careful and say, okay, I'm doing r and theta now. What's the distance from the origin? Well, assuming that each one of these circles is unit 1, this is 1, 2, 3, 4, 5, 6 units away. And what's the angle? Well, the angle is 40 degrees. Now, I really don't want to do things in degrees. I really want to get to the point where we're thinking in terms of radians. So rather than this graph paper, I'm going to slide down here and say, let's start all over again. Let's use this one. I've got this now in radians. Okay, pi over 12, pi over 6. This is essentially your nice angles are the one's in here, and they've got the grid lines on the pi over 12s. Of course, there's grid lines in between as well that just not being drawn. Now let's see if we can plot a point. Let's see if we can say r theta, r comma theta is 3 comma pi over 2. Well, 3 comma pi over 2, it's a distance 3, so the angle's pi over 2. Pi over 2 would be straight up, and a distance 3. 1, 2, 3. These lines are really close together here, but it looks like 3 is right here. Right? It's not being, it's being persnickety. So there we go. There's my point. 3 comma pi over 2. How about something like this? How about something like r theta equals 7 comma 2. Well, what do you mean by an angle of 2? Well, 2 radians. 2 radians is, well, I know 2 pi over 3. Pi is almost 3, so pi divided by 3 is a little bit more than 1. So 2 times, that's a little bit more than 2. So 2 radians is somewhere in, this vicinity right there. Right? So if I have 2 radians of angle and a distance 7 away, 1, 2, 3, 4, 5, 6, 7, I'm talking about a point right here. Okay. Now, a few more examples. R theta equals 9 comma negative pi. So I'm going to turn through an angle of negative pi going this way, all the way back to here, and then I'd go 1, 2, 3, 4, 5, 6, 7, 8, 9. I've got this point. Oh, dang nabbit. 1, 2, 3, 4, 5, 6, 7, 8, 9. That point. That is, when I put an image on this, it behaves differently as I try to move things around. But anyway, notice I'm thinking in terms of x and y axis. I'm on the negative x axis, but I'm calling this r as positive 9, but the angle is negative pi. So I've turned through negative pi, and I move off in a distance r. Now I should point out that I really find it unfortunate that we put these in this order, that I think in terms of the angle first. The angle points me in the right direction. I'm sitting here in my office making this video in my swivel chair, and I'm swiveling, but you can't see me swiveling. But I think in terms of, here I am sitting in my chair, and the angle is going to tell me how far to turn, and I'm looking in that direction, and then it says, okay, now go 9 units in that direction. I go, oh, okay, I'm over here. That is, I spin myself in the direction according to theta, and then I move the distance r. Okay. In red here, I'm going to do another one. I'm going to plot the point r theta equals negative 5 comma pi over 4. Okay. So I'm going to turn through an angle of pi over 4. So starting in 0, the angle of pi over 4 is headed off in that direction right there, right, out in the pi over 4 direction. But I want to go a distance of negative 5 in that direction. Now, when we were doing trig of any angle, we never allowed r to be negative. In polar coordinates, I do want to allow r to be negative. There's a lot of stuff that I can do with r negative. I just got to be able to think of this properly. That if I say, look in the direction of pi over 4 and go negative 5 in that direction, you might think, well, how do you go negative 5? Well, just back up. 1, 2, 3, 4, 5. So I'm at, not that point, right about there. That's my spot right there at negative 5 comma pi over 4. Look in that direction of pi over 4 and back up. This is something that's going to take a little bit of getting used to, of having that negative r value, but it just means face this direction but back up as you're looking in that direction. Okay, so even though pi over 4 is a first quadrant angle, the point negative 5 comma pi over 4 ends up being in the third quadrant because the r coordinate is negative. That being said, in green here, I'm going to plot the point r theta equals 5 comma negative 3 pi over 4. So I'm saying turn through an angle of negative 3 pi over 4. That would be facing this way. And then in that direction, go 5 units. 1, 2, 3, 4, 5. That would get me right there. It would give me right in the exact same spot that this one did. Now this is something that's very different about polar coordinates from x's and y's. Each point in the plane can actually be written with many different pairs of coordinates. In x's and y's, it's unique. If you say I'm at the point xy equals 2, 3, there isn't any other way you could describe that point. But in polar coordinates, you can do it many ways. And I say many ways because, heck, I can say, even with the 5, negative 3 pi over 4, I could have said, turn through an angle of 5 pi over 4, and then go a distance 5, right? As long as your angle is coterminal, and you go the same distance out, you're going to end up in the same place. Or, because we're allowing negatives, maybe your angle isn't coterminal, but it's pointing in exactly the opposite direction, and then you go a negative distance, and you end up in the same spot there, okay? So there's going to be infinitely many ways of writing the same point with polar coordinates. Okay. Sometimes this may seem like it's going to make things more complicated, but actually what it does is it makes things more interesting. There's a lot of nifty stuff we can do, and we'll investigate those in future videos.